Hello, hello. Can everybody hear me? In the back? Yes. Good? Good pizza? Hopefully you're nice and sleepy now. Hopefully. Yeah, so my name is Daniel Dixon. I'm a data engineer for Wells Fargo, and I work with the Advanced Analytics Enterprise Group. So we do a lot of different enterprise-type wide projects. We'll go over our team a little bit. But for me, I'm a data engineer and aspiring data scientist. I do a lot of work with kind of big data pipelines, getting data ready for the machine learning process. I do a lot of work with Spark and Kafka, Hadoop, that kind of environment. But also work very closely with the data scientists in our group. So, I learn a little bit about that as I work with them. And this talk is about how we use AI in some of our projects, and particularly fraud, and with a focus on how we take this, the work that we do, and send it over to production, and how we, what's our role in that as data scientists. All right. So first, the required slide about me. I live in Berkeley, so not too far away. I've been in the Bay Area for about 10 years now, 9 years now. Wow. Before Wells Fargo, I worked with a variety of different companies, mainly in analytics and consulting type roles. Did a lot of work with Tableau, did a lot of work with Teradata and Aster, but always kind of in that analytics world. Got a degree from Georgia Tech, go Jackets, in electrical engineering. Haven't used it since, but I have it, so that's nice. For fun, I like to do a lot of different things. Backpacking is a big passion of mine. Last year, I actually hiked the Appalachian Trail from Georgia to Maine, so that's fun. It was quite an experience. I wouldn't do it again, but I enjoyed it. What is AI? This is a kind of a broad term, and it's used for everything these days. So I think Wells Fargo kind of breaks it down into two different categories: kind of your natural language processing, which is describing meaning from text and speech data, and then also your kind of traditional machine learning, where we look at data and try to find patterns in it and find groupings in it that maybe a human wouldn't intuitively find. So that's how Wells Fargo breaks it down. Why is it important to Wells Fargo? I mean, I think it's important to every company to enable smarter decisioning. Essentially, is what it boils down to. We want to use, we want to make smarter decisions for our customers. We want to use, personalized service. We want to make targeted advertising, all that fun stuff. And that's, that's difficult to do with traditional kind of rules-based approach. So that's kind of why it's important. NLP is not really my domain. So I'll just kind of gloss over the slide a little bit. But it is used within the bank quite a few, in a lot of different places. And these are some of the things we use it for. So machine learning, that's kind of my area. We use all the lines of business kind of use machine learning in some capacity. Tonight we're going to be talking a little bit about fraud. That's the project that's near and dear to my heart recently. But there's also customer experience. We do a lot of targeting, a lot of, it helps make our decisions, and generally just, helps us make sense of our data. And just a quick slide about the team that I work for. Analytics at Wells Fargo is not really centralized. We have a lot of different lines of business, and every one of those lines of business has their own analytics people and machine learning people. So it can be kind of hard to tie that picture together. And our team is the enterprise analytics team. So we work with enterprise-wide type projects. Our customers are usually the lines of business who we work with, and we provide our expertise. But we also work on projects that span different lines of business and different data sets. Some things that the particular lines of business might not envision or see. From their kind of work. All right, enough about Wells Fargo. On to the kind of the meat of this presentation, which is the final mile, taking our machine learning models that we've built and moving them to production. Kind of what's our role with that? So this is, your traditional kind of data science loop that I'm sure everybody's seen some kind of version of this. And if you go to conferences and talks like this, you'll see a lot of stuff in the middle where we talk about cool algorithms and GPUs and big data and stuff like that. But there's very few talks about how do we take those models and push them into production. And especially with maybe larger companies that have more process flows, have more kind of regulations, it can be fairly difficult to take it that last kind of mile into production. So we'll talk about some of the findings that we had in doing just that, and how we kind of overcame them. So there's a lot of different roles that data scientists can take when moving a model into production. I want to focus on two of them here tonight. One is model interpretability. How can we trust what our model is doing? How can we look at it a little more deeply, try to figure out some of the decisions it's making? We want to build trust in our model. We want to know what it's doing. We want to know why it's making the decisions it is, from a regulations perspective, but also just a trust perspective. And so we'll go over some of the ways that we do that. Model monitoring. Once the model's in production, that's not the end of the story. We need to make sure that it's running correctly, that the inputs and outputs aren't changing over time too drastically, and that our model's performing like we expect it to. And if it's not, then we need to take action. All right.
Question.
Sure.
So when you say production, is it mostly sort of batch, or is it you have it in production in some kind of real-time fashion and you're evaluating fraud in real time, some streaming images or something?
It's a mix. This project was a real-time project, but yeah, there's a mix. So the fraud project that we worked on, essentially there's a lot of different processes in place to catch fraud. We're not trying to be the front line to detect if we should stop the fraud or not, but our goal was a little more specific than that. For certain cases, if we're unsure if fraud might have happened, there's a manual review of the case. So a person will go in, look at the case, and make a determination if they think it's fraud or not. And we wanted a way that we could prioritize this so that our fraud agents could catch more fraud, that they were not spending their time looking at cases that might not be fraud, and so that they were as effective as they possibly could. So we built a supervised classification model using H2O and using a GBM model is what we ended up with. The metric that we worked with the business to define and that we optimized to was recall at 40. So if you order all your transactions from most likely fraud to least likely fraud, and you take your top 40%, how much of the fraud are you catching? That's the number that we were optimizing to. And of course, like any model, there's a lot of challenges, especially with the data. And we had a big challenge on labeling our decline data. So this is transactions that come in. We're very confident it's fraud. We automatically block it. And just the way our data is organized and linked within the bank, it was difficult to link those two. So that's one of the challenges that we had, just working with messy data, which I think everybody can kind of everybody's had to do at some point.
One quick question: is it fraud from a credit card processing perspective, or trading perspective, or what perspective?
This in particular was debit card fraud. All right, model interpretability. This is kind of the part one of what we're going to talk about. So we broke it up into 6 different ways that we take a look at our model. And I won't go through these in great detail, but I will touch on them here a little bit. In the later slides, we'll actually go into them. So the first one is segment performance. If you break up your data into segments, how does the model perform in each of the segments individually? Corner cases, can we try to trick the model? Can we pick some of our data that might be tricky for the model, and how does it respond to it? Variable importance, which of my features are most predictive globally? sensitivity analysis. If I start tweaking those features up and down, if I start tweaking those dials, how does my output respond to that? Reason codes, if I want to know why my model is making a certain prediction, you know, I can look at some of the reason codes of why it might be doing that. And surrogate model, which is fitting a much simpler model to my complex model as kind of an approximation, so it's easier to interpret, essentially. Segment performance. So this is something that you work with your business to define, or your data guy, or somebody who knows, you know, what segments that you're working with. Usually there's a report out there that shows what segments that you're interested in. So you find these segments of customers in your data, and you see how your model performs. Maybe it's better than average, maybe it's less than average. So here's some of the segments that we particularly looked at. Brand new cards with no transaction history, those are particularly tough, so you'd expect the performance of those not to be quite as good, just because we have no kind of pattern of their past behavior. Transactions verified by Visa. If transactions verified, then you would expect that there's a higher confidence that it's not a fraud case, so you expect performance there to be better. Long-term customers, you know, might have a longer history with them. You know their patterns of spending. You may know more about them. So those you would expect to do a little better. And it's good to break it down like this, just to see if your expectations match with reality. And if not, you know, why? Yes?
How do we handle false positives? If you decline a transaction, how do you know that it's actually a bad customer?
That's a good question. I don't know how much I can get into the question. Sorry. How do we handle false positives? And you know, how do we make sure that our labeling is correct, right?
Well, if you are doing it in real time, then how do you know that? If you reject a transaction, how do you know that?
So how do we know in real time that our prediction is correct? Is that, yeah, okay. And the answer is we don't. We have to wait, and we've picked a waiting period of 45 days, and essentially we see after that 45-day seasoning window if there's been a claim against it, if somebody's reviewed the case, to define what that label is. So we won't know until a little bit later.
If a customer, say, immediately calls your fraud department and notifies that it was a legal transaction, so how will you handle this? Can you incorporate this into the model faster than waiting for 24 days?
Right. So the question is, if somebody calls in immediately after a fraud has occurred, can we take that more recent information into account? And I don't want to get too much into the project that we worked with. I kind of want to focus more generally, just because I don't know what I'm allowed to say, to be honest. But in general, we have to wait. And that's because we're not, the risk for our model is a little lower since we're not the frontline defense. We're working with you know, more the manually reviewed transactions. So for our particular model, we have to wait. We would like to have some information that's sooner, and we're looking into that.
So it seems like your model is card specific, right? And I would imagine that you're a good model that's generic enough that given similar kind of cards that you've seen before, even newer cards that has no transaction history, that you would be able to predict more.
So I guess the question is, for newer cards, can we compare them to older cards that we have to make more accurate predictions?
Yeah. Well, is your model card specific?
Is the model card specific? Yes, in the fact that some of our features are card specific.
Obviously, you are training the model, so every 24 days after, like, you have a labeling in some way. So it's like pipeline of new data every day. How quickly you incorporate this into the model? How quickly you are training the model?
So how quickly do we get new data into the model as it comes in? Again, I don't want to go into like specifics too much of the particular project, but we retrain the model periodically. And as new data comes in, we look at that. And we also have a history that goes back that we can use to do a lot of our analysis as well.
Trying to understand your graph.
Sure.
So if you have a full data set, you have full coverage, full recall?
Yeah, so this is the recall. So as if you sort your transactions from highest predicted fraud to lowest predicted fraud, and as you kind of go through it from left to right, this is how much of the fraud you actually pick up. Right. All right. And this is just an example. I don't think this is actually real. The second is business corner cases. This is kind of stress testing the model a little bit. We want to find cases where the model might trip up a little bit and see how it does. So in this case, we've picked two different cases where the customer has no transaction history. And to measure that effect, what we did is we took a case that, a fraud case and a non-fraud case. We picked the fraud case that had a high prediction of fraud. We set all the historical features to 0, as if they had no history with the bank, and then made another score on it and compared those two scores. And what we found is that the probability of fraud dropped 20%, which suggests that the historical features are very important for predicting actual fraud. And the opposite of that is a legitimate non-fraud case, where we picked a case that had a low probability of fraud, set all the historical features to 0, and the probability of fraud increased by 2%, which is a really small change, which just suggests that the model doesn't rely on that history to make a legitimate, predict a legitimate case. Variable importance. So this is globally what are my highest features that can predict fraud. What are the most important features globally? And this is important to kind of work with the business to get their expectations, because they know which metrics that they're looking at, and they know the process really well. So when we started this, we got a list of what they thought might be high predictors of fraud, and we compared it to what we saw. And that if they don't match, then that's when you go back and say, okay, why didn't it match?
We also look at the p-values in each case to see if they are statistically significant.
Yeah, essentially. I mean, any kind of machine learning package is going to have give me the most important features. So this is a good way to kind of grab the top 10 or whatever.
Yeah, but it may not be statistically significant, right? So you have to worry about that also.
Sure, but globally, these are the most important predictors. And we'll dive into some of the more local predictors as well.
What accuracy you are trying to reach for the historical data?
Sorry, could you repeat that?
What accuracy for the predictions do you typically try to reach for the historical data?
So what accuracy are we looking for historical data?
Yeah, so for your model, when you verify that your model is reasonable, yeah?
Sure.
You do something on the historical data, and then you want to get some metric or some threshold which
sure.
tells you that it's good to be deployed.
Sure. Yeah, so what we use is recall at 40. So the top 40%, how much of the fraud did we actually catch in that 40%? And I don't know if I can share the specific number, sorry. Yeah, trying to stay general here.
You're like 0.95, right?
Sure, yeah, it's perfect. It gets all of it. And just another point here towards the bottom, if you have highly correlated inputs, depending on which kind of algorithm you use, it can hurt the impact of both or one of them. So it may actually drop in your importance if you have two variables that are highly correlated. So that's just something to kind of watch out for. The next section, sensitivity analysis. What we use for this is partial dependence plots. And if you're not aware what a partial dependence plot is, essentially you pick one of your features and you vary it over its range of values from like lowest to highest for every one of your observations. And you make a score for all those observations, the original plus all the perturbed observations, and then you plot that. And this you kind of get a sense of if I mess with this switch up and down, how does it change the output of the model? And so this can be useful to look at some of your features. But the important thing for this one is you can only do one at a time. So I mean, you could certainly plot all of them, but if you want to plot a certain number of them, this is one where you can look at your global features and maybe pick the top 5 or 10, plot those. You can plot two features at a time, but you can't go really much higher than that without seeing in 4D, I guess. And this is kind of a refinement on the previous method. This is something called ICE. And instead of graphing the average kind of response to a particular variable, you graph individual observations, how they respond to that particular feature. And you can pick any individual observations you want. We picked ones at each 10th percentile. And this kind of shows over our range of prediction values, how does that feature count towards the prediction? How does it respond as you vary that switch kind of up and down? Does it vary drastically, or is it a small amount? Yes?
Are those features interpretable? Like in the sense that if you find that it gets a high fraud score because of these two features, can that help you to interpret the reason that the model created?
Right, and I guess the question is
I mean, are those like PCA component factors that you just don't know what it meant to the physical world, or are those the features that you can actually map to, say, user behavior, certain things that you can corresponding in the real world?
So, not entirely. So, right.
So the features, right? Say like if you, well, maybe I take this off.
You're asking if they're synthesized features, like a combination, like PCA, or something like,
Sure.
the amount of the debit or something.
Sure, yeah. So the question is, are these kind of synthesized features that we calculate based on our kind of baseline features, or are they just your normal features? And it's a mix that we use. And I just kind of want to keep this general mostly. So this is kind of any kind of feature that you might have. Yes?
Since you're observing these features, do they play any impact? You say that this feature is very dominant in the model. Are you going to turn it down? Or you think that this feature should not play that important role and move towards that?
That's a good question. And that's with a kind of a complicated answer, I guess. I would say this is kind of a tool to start interpreting what your model is doing, but I wouldn't take it as gospel, because this won't tell you how your variables interact with each other. That's something that can be a little more complicated. So if one of your features, if it goes up and your model prediction doesn't change, and feature 2 goes up and your model doesn't change, but if they both go up together, and that's a predictive feature, then this won't show that. So you have to be a little careful. This will give you some idea. All right, so this is reason codes, and this is if we want to kind of query the model and say, hey, why did you make this prediction for this particular observation that we're looking at? So these, this one and the next one are observation specific. So you pick a single observation that you want to look at, and it may be find a place where the model is extremely confident but got it wrong. That's a good one to kind of look at. So the way this works is you pick a single observation. And for all its features, you perturb them a little bit, move them up and down for all the features. You can do this in a manual way if you know your data really well, or there's automated ways to do this. And then you create a linear model in the space that this observation is. This is kind of a linear interpretable model. And what that'll give you is, since linear models are very interpretable, you can just read off your coefficients, and that'll tell you the importance of each feature in that local space. So something to kind of know about this one is if you do this, you can understand why it made the prediction for that one observation, but this is not a global model, so this won't show you why the model's working in other places. Another approach is called Loco, and it does essentially the same thing. It gives you those reason codes, I think it's a little simpler to understand. Again, you pick a single observation that you want to look at, and one by one, you leave each of the features out, and then you make a prediction. And you can see how the model responds from its baseline prediction to when you leave that feature out, how the output changes. So this will give you the impact of leaving out that one particular feature. So this does include feature interactions. So if you leave out a certain feature, you'd expect the model to behave in a certain way, but it might not, just based on how your features interact. So this is kind of, whereas the previous approach was a linear model, so it only shows, it does not show interactions. All right, and finally, a global surrogate model. This is where we take a much simpler model and we fit it to our very complex model. So this is a way to approximate whatever our complex model is doing in a way that we can interpret it. So, in this example, we've taken a single tree and we fit that tree to our complex model's scores. And what happens when we do that is we get a model that somewhat approximates, not perfectly, our complex model, but that we can easily, display and that we can look at and we can say, oh, okay, this is how the data is branching. This is what it's doing at each place. So this is a good way to, at a high level, see what your model's doing. Yes?
So over here, how would you know that the tree has fit well to the model?
So you can use the same metrics that you use when you can use, your same kind of accuracy metrics if you want to see how close it is to your original predictions, because you're fitting to the predictions, not what the actual label is. Yes?
So in this one, how much data are you using for decision tree, basically, because unlike the SVM technology, they actually need more data, right? So how much data are you using for this one?
So how much data are we using for this approach? We're using all our data. So we're using all our data for our complex model that's very accurate, but we're also using all our data to fit this simpler model that's more interpretable. So if you can run all your data through it, then yeah, do that.
Okay, so in that case, how are you balancing all the unbalanced data class, because there will be very, very few frauds compared to normal transactions? Sure.
So how do you balance the imbalanced classes problem, especially something like fraud? It's the same approach that you would take with your typical model for imbalanced classes.
So what do? You understand for the goods? How do you correct for?
Yeah, that's a good question. I think it might be a little out of scope, and it's using the same approaches that you might for your initial model. This is just if we want to understand how our model is functioning, we can use those same approaches for this simple model that we use for a more complex model. So the next section is the monitoring. Once it's over in production, how do we make sure that it's still running? How do we do that? So we've defined it in 3 different ways. The error handling, what kind of errors are our model throwing? Is there missing data that's coming in? Are there unseen categorical values? Are we still scoring missing data? And how often? So these are the kind of things that you want to know over time and that you want to maybe go back and correct at some point. But you definitely want to know what's happening. The next is operational stability. Are inputs and outputs stable over time? The model's expecting a certain distribution of data to function correctly, and if it's not seeing that, then you might want to do something. And finally, prediction performance. How accurate is our model over time? Just data drifts over time. Our model degrades typically, so you want to know when our performance has dipped below a certain threshold, which we can define. So you definitely want to log all these things and monitor them over time and have some kind of thresholds for when you take some kind of action for this. So for variable monitoring, we use a lot of different tests. So we use a combination of these statistical tests. So there's a couple of basic kind of summary statistics: your mean, your standard deviation, your quartiles, and your min and your max. But we also use some more, advanced distribution type tests. to test if a distribution of data has changed. Typically, something like this would be a Ttest, but we use something that measures magnitude, and I'll get into that. But we also do some stuff with histograms, and we break our data set into deciles. So if you take each one of your features and you order it from highest to lowest and give 10 buckets and put all your data evenly in each one of those buckets, how do those buckets change over time? Because you would expect them to have the same amount of data in each one. And how does it change from the data that I trained on versus the data that I'm seeing in production? And we use something called population stability index to measure that. And then there's some other tests that we use here. We're going to go into the one that's circled.
What do you do if you will find some difference between an expected data set and what you were trained with? So how you would proceed with that?
Sure, yeah, and that's a complicated question, but it's a good question. And the question for those who may not have heard, it's what do you do when you see a difference and kind of how you make that decision. You pick thresholds just based on. At first, it's essentially just an educated guess, and then over time you can refine that guess. But you pick a threshold that you'll do something. And what we did is there's a threshold where we'll go back and look at it and do some analysis, and there's a threshold where we'll stop and we'll say we're not going to score any more, anything more with this model. And so we've defined those thresholds beforehand, and over time as we monitor this, we'll refine those thresholds. So testing if two populations are the same. Typically, the way that you do this is a Ttest, where you calculate the difference of the means over the variance, and this will give you a statistical likelihood that the two populations are the same, whether it's just kind of an accident of your sampling or whether it's the two populations are actually different. And for this test, it depends on the size of the effect, so how different the two populations are, but also the size of the different samples for both of them. And so what we've kind of found is that when you start working with larger and larger data, the Ttest kind of breaks down, and it's no longer a good predictor. So what we used is something called Cohen's D. I have no idea what the D stands for. But in this case, we're measuring the magnitude of the effect. So how large is the difference? Not whether it's statistically significant, but how large is it? And there's a couple different formulas for it, but what we've used is the difference in means over the standard deviation of the control set, which in our case is our training set. And this will give us a magnitude of how different our control set is to our production data that we're seeing. And we'll measure this over time. And if it gets above a certain threshold, which we arbitrarily define, then we'll take some action on it.
What kind of action do you retrain certain parts of the model?
It's a good question. And the question was, what kind of action do we take? And it depends on how big the difference is. We have a threshold for somebody going in and looking at why it might have changed. Did our inputs change significantly or something like that? And then there's a threshold where we'll stop. And we'll go back and figure out what to do, either retrain or build a new model, something like that.
And also, do you phase out all data over some period of time?
We do, yes, yeah. We're typically training over about 30 days of data, but we use a folding scheme where we're looking at data over time. So we use 30 days, but we use 5 different periods of 30 days to do our analysis. Yeah. And then just a shout out that we're always hiring. So if you enjoyed the talk and what we're talking about, we would you can go to this website and see what kind of opportunities that we have. We're always hiring, and especially in the kind of analytics world, where I would say we're aggressively hiring. So there's always openings there. So go to that website, and there's a handout up here if you want to know some more information with this link on it. So yeah, we would love to work with you. All right, thank you. And are there any questions? Sure.
So based on the predictions that you make on a particular transaction, you end up for the transaction on your start, right? That's the action that you take on the transaction.
Sorry, I'm having a little hard time hearing you.
Let me get you a mic.
Thank you so much. So the action that the bank takes on a transaction based on this predictive model's decision that, hey, it's going to be fraudulent, stop it. So somebody's going to take a call saying that, okay, automatically it'll stop. Now, if as a customer, my transaction is stopped, do I get to see it? And if I go and call your helpline saying that, why did you decline my transaction? What is the kind of answer that I would get as a user?
Right. So the processes we have in place are pretty complicated. This is not the frontline model. So this is not the model that will automatically catch and call you or block the transaction.
I see.
This is not that model. This model's job is to help prioritize the manually worked cases. So when somebody has to go and look at it and manually spend time looking at it, and that's what this model's for.
Okay, thank you.
Yeah, great talk. I'm just wondering what are you dissatisfied? What's the room for improvements going forward? Like, what are you dissatisfied about Small that you're trying to improve?
Sure, all of it. Yeah, there was a lot of learning along the way. I think the biggest challenge that we had is just the data. I don't even think it had anything to do with data science or machine learning. It's just getting the data sets that are spread out, getting them together in one place and making sense of it. So I think we're still we're working with that. There's a lot of other features that we want to bring in to make it more predictive for sure. So yeah, I would say that, just the extra features that we didn't get around to including the first time.
Since you use kind of like a manual review process, do you get any inputs from the people who do a manual review on why they think that this transaction is suspicious? And can you somehow apply kind of meta-analytics so that you would try to identify patterns in decisions made by the people to figure out how we can?
Sure. So the question is, do we get any feedback from the manual review process, especially around why they think the fraud occurred, and so we can bring that back into the model and make it smarter? And the answer is not today, but we want to. Yes.
What is GDPR that you like in terms of accessing?
Good question. It's probably above my pay grade, but I think a lot of Wells Fargo's operations are here in the United States, so we are certainly affected by the GDPR. But I'm guessing, since this model is not frontline, that we're not directly affected by it. Yeah, so it's to help optimize internal processes, so it's not gonna face the same.
To the patient, not patient, but customer activities, which I believe is still regulated.
Yeah, I'm not sure. Sorry. In the back?
Yeah, so for the interpretability and this maintenance. So for the, after you train your model, how much of the maintenance work for interpretability and the performance monitoring, how much of that is automated versus hand-tuned?
That's a great question. I would say it's about half and half. We have about half of the work automated and half of it is manual, but we're working to make more of it kind of an automated process. Yeah.
Oh, sorry. The question is, did you, in your model development, did you take into account seasonality or timing of, for example, summer vacations or holiday periods, et cetera, into the development of the model?
We did, yes. And that's some of the analysis that we did when we looked at segment performance and also corner cases. We looked at holidays and seasonality as well over time. So yes, we took some of that back into our model.
Also about identity theft kind of cases, how did you guys take that into account, and how was the model trained to get into people who get ID thefts?
That's getting a little model specific. I don't want to get into the data too much. Yeah.
Okay. Thanks.
So were there any optimizations done for speed, basically, to make sure that the model can process data faster?
Sure, yeah.
Because fraud, you want it to be real time, though, like it's not frontline, but still.
Absolutely, yeah. So we're working with a lot of data for this particular model. So the training itself is batch oriented, but when we're scoring, we're obviously it's real time. The training itself, we were really helped out with. We used Spark to do our data crunching, and we used H2O to do our machine learning. So a lot of the work that we did there is distributed, which really helps. But the training is a batch process, and then the scoring is. We took that process to just basically a Java workflow that scored the data.
You have a question? Sorry, just to follow up on that question, could you give us some idea of the hardware that you're using for all this work?
Probably not, sorry. So is this kind of an could you repeat the? Right. So for a model like this, since it's very kind of internal to the processes that we run, it's not kind of your run-of-the-mill fraud, is it? Right. I'm guessing you won't find a lot out there about companies talking. Probably. Yeah, I'm not sure.
Hello. Well, I have a question about the balance in training data, like in the fraud case, and if like 90% of data are not be frauded, but only like 10% are frauded. So typically, what you guys deal with those kind of data?
Right. Yeah. So your unbalanced kind of classification. We use H2O's algorithms to do this, and they have a lot of features for working with imbalanced classes, weighting or oversampling, undersampling, and we use one of those.
Do you account for a fraud from your customer? Say somebody made some transaction and called the bank said I didn't do that, and you don't know whether it was real fraud or it was like a fraud from your customer. Do you somehow like have this labeling?
Sorry, could you repeat that?
I mean, if one of your customers, the owner of a debit card, made a transaction and then called bank said I didn't do that.
Right.
So how will you somehow handle this case specially?
So if a customer has fraud on his own account, so the customer is making the fraud by himself?
I mean, he did a transaction, and when he tries to somehow cancel his transaction, saying that it was a fraudulent transaction.
Right.
And you don't really know if it was or it wasn't. And maybe he did that for some purpose, and then he cancels this. So would you be able to distinguish that?
Yeah, so I mean, we're going to look at we're not going to look at the claim until it's finalized. So if the customer calls in, that starts a claim, and then we'll either manually review it, or there's a lot of other processes that determine if we decide it's actual fraud or not. But that happens later. What we're going to do is we're going to look at the data and determine if it's fraud minus the customer calling in, and then we're going to make that determination, and basically say how confident we are in it.
Okay.
Yeah.
Yeah, just give me a minute. So what percentage of data is, do you see outliers, and how do you deal with that?
That's a great question. I think it's a little out of scope for this talk, but we did see some outliers, and we did handle them. Typically, with the size of data we're looking at, it's typically not a huge problem, but we did exclude some outliers in our training, and we have ways to detect that in our real-time scoring as well.
Okay, thank you.
More questions?
Going once. All right, thank you.